Welcome back. This is chapter 5.2 on atomic spectra and energy levels. So some really cool things happen when you give energy to electrons, to atoms. The electrons go nuts. So imagine putting some chemicals in a fire. You might get green, or you might get purple, or you might get red. Okay, don't put stuff in your fireplace. Or I see here, these are neon lights. Neon is simply a gas, and if you give that energy by putting in an electricity through the gas, then you can generate a color and make a sign out of it. Okay, so like we're open or something like that. So some really cool things are happening, and I'll try to explain some of it in a minute. First thing we need to look at is the idea of a photon. So we've already talked about light being a wave. So light has a wave property. So there's an oscillation, kind of a sine wave, an up and a down and an up like a guitar string, out and back the other way, or a swing set as it's going back and forth. But what is also true of light is that it also is the idea of a packet. So it's a particle. It's a thing. It's an object. It actually has mass. In fact, a black hole is called a black hole because light, it's so massive that it even sucks light into it, and light doesn't escape from it, and you can't, and that's why it's black. Okay, because light doesn't even go, light goes in but can't come out. So light is so tiny, and you wouldn't even think of it as an object. You'd think of it just as energy. But you can think of it as both. It has a dual nature, the duality. So it is a wave, and it is a photon. Now, the 20th century physicists actually stretched that a little further, and if you've ever watched Star Trek where they beam people up, if I can throw you out the window fast enough, you will travel like light. You'll travel like a wave where you'll go back and forth and back and forth. Matter has waves. So that's pretty clever. So both are true at the same time. Light is a wave, okay, energy wave, and light is actually a thing called a photon. So a photon, Greek photos is light in Greek. So it's a packet of energy, okay? It's traveling at the speed of light in a wave, but when it hits something, then it would act just like water on a water wheel. So you can have a solar-powered calculator, and that light striking that plate can give enough energy to your calculator to make it work. Okay, so it has high energy, short wavelengths, and low energy has long wavelengths, but it's still a photon. So it's a packet and it's a wave at the same time. Now, the spectrum, if you were to see light coming through the window, and you've ever seen it split, say there's oil on your driveway and you're spraying the water hose and you can see it all iridescent colors, or even a soap bubble like that where it'll all split up, or through a piece of crystal or a prism where light's passing and it'll make a rainbow. What's happening is that light coming through the window is all the different colors of light coming from the sun. And then, so white light is a accumulation of all of those wavelengths. If it passes through a prism, it can refract that light, which it bends it, and then separate those colors. So a spectrum is that rainbow, or that all of the different colors from long. So the red bends, is very massive and doesn't bend very much. Purple is very light and bends a lot. So you're going to see that it would spread long to short. Okay, so in this case, you've got some barium flame, and that barium is going to have a fingerprint. Now, this is pretty cool. Every element, if you heat it, is going to produce only certain wavelengths of colors. All right, so if you were to pass white light through a prism, you're going to get a full rainbow, Roy-G. Biv. If you pass mercury light or barium light or chlorine light or fluorine light, you're not going to get the whole spectrum, or you're only going to get certain wavelengths that's going to be produced. So in this case, I guess they're right here, barium is going to produce only five in the red range, okay? Then you've got 3 in the orange, 2 in the yellow, 2 in the green, 1 in the blue, 1 in the violet. And that is the fingerprint of barium. In fact, if you were to look up into a barium light through a oscilloscope or through a spectroscope, you're going to see it split like that. And you could look at something you don't know, and if you had a table where it had all of the different fingerprints, you could say, oh, that's barium, or that's fluorine, or whatever. What is happening here is absolutely awesome. If you give an electron some energy, it's going to go nuts. It's going to be hyper. It's like giving a hyper kid sugar, okay? So let me try to explain it to you if I can. So let's say that I've got a nucleus of an atom here, and I've got an electron that lives out here. That electron normally is at the speed of light, almost the speed of light, whirring around in a shell around that nucleus. If some energy comes, so let's say that I've got some light energy or some radiation of some kind, some gamma rays or microwaves or any kind of radiant energy, it's going to absorb it in that electron. That electron is going to absorb the energy, and the electron is a thing. It's an object, so it can't really change any, but it can go nuts. It can go faster. And by going fast, it's already going the speed of light at a low orbit, so it can't go faster than it already is. So what'll happen is it'll jump out to a higher orbit and go the same speed. So it won't go faster, but it's traveling a bigger circle because you've given it energy. So it's now temporarily way out here. Okay, the more energy you give it, the higher that electron gets nuts and goes out. All right, but the problem is that electron doesn't live there. The electron is here. The electron in whatever atom you're talking about is wherever it normally is. And if you temporarily give it some energy and make it go to an energized state, it's eventually going to have to collapse. And if it does, it's going to emit the same amount of energy that it absorbed. It's like the quarter at the Aldi's. When you go to Aldi's and you put the quarter in the cart and you get a cart, and then you're done with the cart, you put the chain back in it and the quarter comes out. The same amount absorbed is the same amount released. So let's say it absorbs enough energy to come out to here and then eventually falls back. Where does the energy go? It's going to emit a photon of light. And the photon is going to have the same wavelength as the photon that came in. Okay? Now remember, light is not always just visible light. It's any electromagnetic radiation. Okay? So it can be anything. It could be in light, or it can be in infrared, it could be in ultraviolet, it could be in microwaves, who knows? But whatever it absorbs, it releases. Okay? Now, it doesn't have to release all at once. Let's say that you absorb $10. You could drop back $2 and then drop another $8. Okay, so it's almost like a ladder. Let's say that here's the nucleus, and here's where my electron lives. If I absorb some energy into that nucleus and it jumps all the way up to the 5th level, okay, let's say it absorbs $10 worth of energy, whatever $10 of energy means. It'll jump up to the 5th level. Well, if it jumps all the way back to the nucleus, it'll throw $10 of wavelengths out. Whatever frequency it absorbed, it will emit that same frequency. Or it could break apart and emit a couple. So $10 can be 2 and 8, or 1 and 9, or 4 and 6. You can drop it up, or you could separate it into several. So for instance, if it goes down to here, it'll emit a smaller wavelength, or a lower wavelength, something that's not as energetic. And maybe this could jump all the way down to here, and this is still less energy than the original. And then eventually it falls back to normal and it'll emit. So these three would add up to the same amount of energy that the nucleus originally absorbed. Okay, so here it is. This is absorbed. Okay, it's at a new energy level. Let me do it in yellow. Okay, it's at a new energy level. When it falls back to its normal, it emits light, and it emits it in the same frequency that it absorbed. Okay, so let's say it falls a short distance, it's going to emit a low light. Remember, low would be red or orange. Okay, if it falls a higher distance, it's going to emit a higher wavelength, which is higher energy, so it would be like yellow or green or blue. If it goes even farther, it might even not even be light. It might be ultraviolet, or if it's farther, it might be even more like X-rays. Okay, so it's going to absorb and then spit back out. Okay, so for instance, if it goes from 3 to 2, it's going to emit an energy equal to the difference between those two energies. Okay, so it goes up to the $10 ladder rung and then drops down to the $8 ladder rung. It only used 2 of its dollars that it had extra. Now it has 8 more to fall. And it can fall another 2 and emit another wavelength, and maybe another 2 and emit another wavelength, or it can go all the way to the bottom and do a different one. So the wavelengths it emits is equal to the energy that it falls. But just like you saw that it was a ladder, there's something called quantization. It's not like a ramp where you can walk anywhere. A ladder, you're either on the first rung or you're on the second rung. You're never in between. You can't stand between the rungs of a ladder. You can only stand on the first or the second or the third. So you go up to a certain energy level and then fall back to a previous energy level, and then whatever that amount of energy was, you'll emit a wavelength of equal energy. Okay? So ultraviolet, which you cannot see, can fall, say, from the 7 to the 1, or 6 to the 1, or 4 to the 1, and that's UV. Visible, if it falls farther, it's going to be that higher energy level, like violet. If it falls just a shorter distance, it'll be a lower energy, longer wavelength, like red. Infrared, can't see it. It's just heat. So here's a learning check. And each of the following energy level changes indicate if the energy is absorbed or emitted or not changed. Okay? So if it goes from the 1 to the 3, it must have absorbed energy in order to get to the third rung. How do I go to the third rung? I need more energy to get taller. Okay? If an electron falls from the third to the second, well, then it releases energy. Okay, because it had high energy and now it has a lower energy, so it goes away. And if electron moves within the third level, then nothing happened. It still has that same amount of potential energy. So check yourselves, and I hope you have a great day.